Hello friends, so today we are going to solve the questions from heat and thermodynamics, and these questions are from the year 2012, 3 questions, and from 2013 we are having 2 questions, and these 2 questions are from the advanced part for the year 2013. So in total we are going to solve 5 questions. So the first question, it was asked in the year 2012, and it states that 3 very large plates of same area are kept parallel and close to each other. They are considered as ideally idle black surface and have very high thermal conductivity. The first and third plates are maintained at a temperature of 2T and 3T respectively. The temperature of the middle, that is the second plate, under steady state is. So we are given that we are having 3 plates, so we can just draw an approximate figure for that. This is first plate, and this second plate, and this is a third plate. First, second, and third, and it is given that the first plate is having a temperature of 2T and our third plate is having a temperature of 3T, and we are supposed to find out the temperature of middle plate. Let us suppose we call this as 2T, T2. Okay, and we have to solve this under steady state condition. So under steady state we can say for the specifically this middle plate that our net radiated heat transfer to the middle plate is equal to 0. So we can write it out that under steady state net radiative heat transfer to middle plate is 0. Okay, or in the we can say our in terms of equation, or we can say that basically it's an energy conservation but written in a different format. We can say that the energy absorbed or heat absorbed will be equal to heat emitted. Okay. And we know that the plates are given as ideal black bodies, therefore we can use our Stefan's-Boltzmann law. So we can say we are going to use Stefan's-Boltzmann law. Okay. And our middle plate is going to absorb the heat radiation or radiation from first plate as well as second plate. Okay. So first plate is going to send the radiation towards our second plate. Similarly, third plate is also going to send the radiation toward the second plate, and our the second plate is going to emit the radiation from both sides also. Okay, so it is going to emit the radiation from the one side as well as from the other side also. Okay, so it is going to absorb from our first plate and third plate for its respective surfaces, and it is going to emit the radiation from our both the surfaces. Okay. Therefore, we can write that according to Stefan-Boltzmann law, we can say that power absorbed by middle plate, okay, per unit area, that will be equal to, for our power because of first plate plus power because of our third plate. And let us say that this is equal to our PA for the second, power absorbed by the second plate. Thus we can write that power absorbed by our second plate will be equal to, for the first plate emitted will be equal to our Boltzmann constant, its temperature, and we have this raised to power 4. Okay, this is per unit area, so we are not going to count the area because area will be same and it can later on cancel out also. And this is sigma, we have this is 3T whole raised to power 4. And now we come to the power emitted by the middle plate. Power emitted by middle plate. Okay, and it will be from both sides, from both sides. So we can write as a power emitted for our second plate will be equal to twice because of the both side, and this comes as sigma, temperature we assumed at T2 whole raised to power 4. Okay. And this power absorbed will be equal to power emitted. So we can say our power absorbed by the second plate will be equal to power, let me write in capital E, emitted, power emitted by the second plate. Therefore we can write this as our sigma, and we have this as 2T whole raised to power 4 plus sigma 3T whole raised to power 4 is equal to twice sigma T2 whole raised to power 4. And this sigma cancels out throughout. Now it is a simple calculation. We get this our 16T4 plus, and this will be 81T4 is equal to, this comes as 2 temperature T2 whole raised to power 4. And 16 plus 81 will be equal to 97. So this comes as 97 T4 is equal to twice T2 whole raised to power 4. Therefore we get our temperature T2 will be equal to 97 divided by 2, and this comes as our 1 by 4 multiplied by T. So this is the temperature of our middle plate. So we get option number C is the correct one. Option C is correct. Next question. It was asked in the year 2012, and it states that a mixture of 2 moles of helium gas atomic mass 14U, and 1 mole of argon gas atomic mass 40U is kept at 300 Kelvin in a container. The ratio of their RMS speed is. So this question is directly based on the formula. We know that our RMS speed formula Vrms is equal to square root of 3RT divided by M. Okay. And here M is our molar mass. Okay. R is our universal gas constant and T is the absolute temperature in Kelvin. Okay. So we have two gases, so we can divide this formula into two parts. So we can write our Vrms for our helium will be equal to 3RT mass of helium square root. Similarly, we can write this as Vrms for our argon will be equal to square root of 3RT and mass of our argon. Simply take out the ratio and we can write that our Vrms helium and Vrms argon will be equal to, and this will be coming as our 3RT mass of helium and 3RT mass of argon and its square root. So this 3RT cancels out, so we get this as our mass of helium, and we have our, rather we can say molar mass of, okay, molar mass of argon and its square root, which is given to us, that is 40 and 4 square root, and this comes as square root of 10, so we can say which is approximately equal to 3.162. Okay, so this is the ratio of their RMS speed. Next question. It states that it was asked in the year 2012, 2 moles of ideal helium gas are in a rubber balloon at 30 degrees centigrade. The balloon is fully expandable and can be assumed to require no energy in its expansion. The temperature of the gas in the balloon is slowly changed to 35 degrees centigrade. The amount of heat required in raising the temperature is nearly. So in this case, we are given that balloon is there and it is fully expandable. Okay, it means it cannot be further expanded. And then the temperature is raised to our 35 degrees centigrade, and we have to find out what will be the heat required to do this rise in temperature. So first of all, we have to identify what will be the process, and in the process we are given that our balloon is fully expandable. And which basically means that no energy is required for further expansion, or we can, in shorter term, we can say it cannot be further expanded. It cannot be further expanded. So it means the pressure inside the balloon is constant. So we can say pressure remains constant. And if pressure remains constant, we can say we are going to have a isobaric process. We are having isobaric process. Okay. And so we can use the basic, because pressure is constant, so we can use the heat required formula NC of P times delta T. That we are going to use our standard formula. And the various things that are given to us, we can just write it down. We are given number of moles, that is N is given, that is our 2. We are given initial temperature. Initial temperature is our T1, which is given 30 degree. So this is our 303 Kelvin. We are given a final temperature, that is our T2, and that T2 is 35. So this comes as our 308 Kelvin. And from here we can find out the change in temperature, that is our delta T will be equal to our T2 minus T1, which is our 308 minus 303, giving us 5 Kelvin. Okay. And the gas is said to be helium, so it is basically monatomic. So we are going to have a monatomic gas. Okay. And we can write that for our constant pressure, we can say heat required in an isobaric process that is our Q will be equal to N C of P multiplied by delta T. C of P we can easily find out. Okay. C of P we know is equal to C of V plus R, and C of V is our 3 by 2 plus R, and this comes as our 5 by 2 times R. And we substitute, we get that our Q number of moles is our 2, C of P is our 5 by 2 times R is our 8.3, change in temperature is our 5. So we get this Q will be equal to our 207.5 joules. So this is approximately 28. So option D is correct. Approximately 28. So we can say option D is correct. D is correct. Next question. It was asked in the year 2013 advance, and it states that the figure below shows the variation of specific heat C of a solid as a function of temperature T. The temperature is increased continuously from 0 to 500 Kelvin at a constant rate. Ignoring any volume change, the following statement is or are correct to reasonable approximation. So we say multi-correct it can be. Okay. And we are given that it basically increases at a constant rate. Okay, from the graph we can see it is basically a constant rise with respect to a specific heat as well as our temperature. Okay. So we can say that our temperature increases at constant rate. Therefore we can say that rate of increase of temperature, let us suppose, is a constant K. Okay. This is a constant, and because the heat will be given to a solid, therefore we can say that the heat absorbed by the, or we can say rate of absorption of heat per unit mass. So we can say our rate of absorption per unit mass. And that is our dq by dt, which will be equal to our specific heat, which is our temperature dependent, and this is our rate of change of temperature. So we can write this our, let me write this as C only, otherwise it will be C, and this dt by this rate of change of temperature we can substitute by constant K. Okay. And if the temperature increases from T1 to T2, we can write that total heat absorbed over temperature T1 to T2, and we can write this as Q will be equal to integration T1 T2 C of our dt, and which is basically nothing but our area under the curve. Area under the curve. And so let us check these options one by one. So it states that the rate at which heat is absorbed in the range 0 to 100 Kelvin varies linearly with the temperature T. Okay, so we have to find out between this 0 and 100, it is varying linearly. Okay, graph doesn't represent the linear relationship, but we will try to prove it mathematically if possible. So we start with option A. And we just wrote that our dq by dt is our C times K. And we know that if our this dq by dt, if it should be varying linearly, then this our specific heat should be proportional to our temperature T. Okay, according to some question, you can say if we use some type of constant also. Okay, let me write it out, then we can discuss it again. So we can say for dq by dt to vary linearly with temperature T. Okay, basically it means that for linear relationship our dq by dt should be proportional to temperature T. But on the right side we have a specific heat as well as constant K. So it means this specific heat should be proportional to our temperature T. Then only on the right side that this T can be accommodated. Okay. Or from here we can say that is this C should be equal to A times T, okay, where A is our some constant, okay, any constant. Therefore, we can write that our dq by dt will be equal to A times T times K, or we can write this as our AK times T. Okay. And at the low temperature, we can write that our at low temperature, which is 0 to 100 Kelvin, there is a model which is called as a Debye model. Okay. So we can say at low temperature 0 to 100 Kelvin, the Debye model suggests that our C is proportional to T cube. Okay. And okay, and we have to this, let me write it in. Okay, so this proportionality is for insulators, okay, and for our, you can say this C is approximately equal to our gamma T plus beta T raised power cube, and this relationship is true for our lattice contribution. Lattice contribution. Okay. So because in the question it is mentioned that we have to make a reasonable approximation. Okay. So based on this, we can say that our dq by dt is proportional to our temperature. This is reasonable approximation. We are not very sure about whether this relation will hold or not if it is not mentioned. Okay, so there is some doubt about this reasonable approximation, but based on this we can say option A is correct, okay, because we assumed that this C of this particular relationship of our C is linearly approximated as our T. So we can say option A is correct. Okay. Now we come to the option B. It states that the heat absorbed in increasing the temperature from 0 to 100 Kelvin is less than the heat required for the increasing the temperature from 400 to 500 Kelvin. Okay, so we are going to find out the difference in or make a comparison the amount of heat required for raising the temperature. Okay. So we can say heat absorbed for our, we can say our Q, when the temperature is going to from 0 to 100, it is given as our 0 to 100 C and D of T, and we have this is Q, which is from 400 to 500 will be equal to 400 500 C of dt. Okay. So it means basically we can say that we are making a comparison about our area under the curve. Okay. This, like we said, this is the area under the curve for the range 0 to 100, and this also represent area under the curve which is for our 400 to 500. Okay, but in this both cases we can easily see that the temperature difference is 100. In this case also, first case also, temperature difference is 100. In the second case also the temperature difference is 100. Okay, but there is a, you can say, a law which is called as a Dulong-Petit limit. So you can say that our Dulong-Petit limit, based on which the graph is there, which states that our this C increases with temperature at low value of T and levels off at high T, which we can say from the graph also. The graph is given for the higher value of T. You can easily see that value of C becomes nearly level off, meaning it becomes constant, and for the lower value of T it is continuously increasing. So this distinction we can make from the, this is basically our Dulong-Petit limit. Okay. And therefore we can say that you can say in option A we just said that for our lower range, that is 0 to 100 Kelvin, this C of T is nearly linear, approximate linear. Okay. So we said that our 0 to 100 Kelvin, we are having that as C versus T is approximately linear. Okay. And for the range 400 to 500 Kelvin, this value of C is large. Okay. And approaching a constant value. Therefore we can say that the area for our 0 to 100 will be marginally less as compared to the area which is from our 400 to 500. Okay. Thus this option is correct. Okay, because this we said is representation of our area. Okay, this represent of our area as well as this also represents of our area. So area of our 400 to 500 is greater. Therefore the heat required will be higher at 400 to 500 marginally, but it's still there. And we come to the option C, and there is no change in the rate of heat absorption in the range 400 to 500 Kelvin. Okay. So basically it means that it should be our constant. Okay. And from the graph we can also see that there is no rate of change of absorption. So this, from the graph we can make a random guess that with this range our C is our nearly constant. Okay, so we can say dq by dt is our constant. So we have our option C, and like we said that our dq by dt is our C multiplied by k, and C is nearly constant, so this entire product will be equal to some constant value. Okay. Therefore we can say that our option C is correct. And it says that the rate of heat absorption increases in the range 200 to 300 Kelvin. Okay. So from the graph also we can clearly see that there is a increase, so this option is also correct. Okay. Because this is based on a reasonable approximation, so this reasonable approximation is a little bit, you can say, not easy to make a conclusion. We can make a very broad conclusion based on this reasonable approximation. Okay, so in this case all the options are correct. So option A, B, C and D are correct. Next question. It was asked in the 2013 advance, and it states that 1 mole of monatomic ideal gas is taken along two cyclic processes EFGE and EFHE as shown in the PV diagram. The processes involved are purely isochoric, isobaric, isothermal or adiabatic. Match the paths in the list with the magnitudes of the work done in the list. Second, select the correct answer using the codes given below. So basic graph is given to us. So we are given that the process starts from E and comes back to E by two processes. One is go from E, F, G, and then through H comes to E, and otherwise it comes as our E, F, H and E. Okay. And it is mentioned that the processes involved are isochoric, isobaric, isothermal or adiabatic. So two processes we can easily identify from here. One is isothermal. So isothermal we can say, sorry, not isothermal, but we have a constant volume. Therefore we can say that our this Fe will be our constant volume process, whereas He will be our constant pressure process. Okay. And there are two processes which are remaining to identify. One is our isothermal, other one is our adiabatic. And we know these two are comparatively we can identify them with the help of the slope. Okay. And for slope we can say that our we have two processes Fg as well as our Fh. Okay. And we know that our adiabatic processes are much steeper as compared to isothermal. Okay. So which basically means that our this Fg will be our isothermal process and this our Fh will be our adiabatic process. This we can identify by making a comparison of their slope if they are given side by side, otherwise it will be difficult to identify them. Okay. So we can say that our we can write that our adiabatic process are steeper than isothermal. Therefore, we can write that our Fh will be our adiabatic and our this Fg will be our isothermal. Okay. And rest two we know is our one will be a volume constant, other one will be our pressure constant. Okay. And so let us first of all use our Fh and try to find out our, because here for this Fh we know our initial pressure, final pressure, and initial volume we know, final volume we don't know, which we are going to find out. So we are having our F, which is at 32 P naught and V naught, and this goes to H, which is our pressure is our P naught, and suppose volume is we taken as our VH. Okay. So we know that for adiabatic process we have that our PV raised to power gamma is equal to constant, and we are given this as a monatomic, and therefore we can write our gamma is equal to 5/3. Gamma is our 5/3. So according to this we can write that our P of F, volume at F raised to power gamma, is equal to P of H, volume of H, and raised to power gamma. And we simply substitute P of F is our 32 P naught and V of F is our V naught whole raised to power gamma, or we can write this as 5/3 is equal to P of H is our P naught, and this comes as our V of H raised to power 5/3. Here P naught and P naught cancels out, so we get this as our V of H will be equal to, this will be over 8 times V naught. And now come we to process Fg, which is of isothermal. So So we have our process FG, isothermal, so which basically means temperature is constant, and I think we need to find out. So everything we need to find out for each process, we are only going to find out the work done. So let's find out the work done. So we can say work done for our Fg will be equal to nRT natural log of, we have our P initial divided by P final, or as temperature is constant, so we can write this in the form of volume also, and or one second, let's write in the pressure form, because initial and final pressure we know, and we can write number of moles over 1, so this comes as 1 RT, we can write as our PV is equal to nRT, ideal gas law will be giving us 32 P0 V0, and we have this natural log of initial pressure is our 32 P0 and final pressure is our P0. So this P0 and P0 cancels out, so we get that our work done from F to G will be equal to 32 P0 Y0 natural log of 32, and natural log of this 32 we can write 2 raised to power 5, and 5 can become outside, so this becomes 32 multiplied by 5 P0 V0 natural log of 2. Therefore we get our work done for the process from F to G will be equal to, and this comes as 160 P0 V0 natural log of 2. So the work done for our Fg, and work done for Fg is our S, and it gives option number 1. Okay. So you can say S matches with 1. Okay. And let's go for our work done for our GE. Work done for our GE is basically our isobaric process. GE is our pressure is constant, that is P0. So we can say our process GE, which is isobaric and pressure is constant, therefore we can say that our work done for our GE will be equal to pressure multiplied by rate of our change of volume, which we can write our final volume minus initial volume. And we already found out our volume, and we can write this in terms of our pressure is our P0, and we have this as a VE minus VG. Okay. And VG we found, VG we don't know. Okay, we need to find out our VG. One second. Okay, we can find out of Vg, not a big issue. And let me solve for Vg, and we know that our process Fg is isothermal. Okay, let me solve it here. So we know that our Fg is isothermal, therefore we can write that our Pv is equal to constant, okay, because the process Fg is isothermal. Okay. Therefore we can write that our pressure at F, volume at F will be equal to pressure at G, volume at G. And pressure at F is our 32 P naught, volume is our V naught, is equal to pressure at G is our P naught, and volume at G, let us suppose Vg. And this P naught and P naught cancels out, sorry, this P naught and P naught cancel out, so we get that volume of G will be equal to 32 times V naught. Okay. So now we can just substitute. We get this as our P naught, VE is our V naught minus 32 times V naught, and this comes as our minus 31 P naught V naught. Okay. And if we take the magnitude only, so we can say our work done from G to E will be equal to 31 P naught V naught. And for G to E is of 31, so option 4 is correct. So P gives us 4. Okay. And we are now with our FH, and for FH is our adiabatic process. So we can say that our process FH, which is adiabatic, and we can write that work done for FH will be equal to pressure at H, volume at H minus pressure at F, volume at F divided by gamma minus 1. Okay. And we know that pressure at H is our P naught. So this is our P naught, VH is our 8 times V naught minus pressure at F is our 32 P naught and times our V naught. Gamma is our 5 by 3 minus 1. And now this is quite straightforward. We get that our work done for F of G will be equal to minus 36 P naught V naught. And for magnitude only, this will be equal to 36 P naught V naught. So we can say from F to H is 36 P naught. So option 2 is correct. So R goes with 2. And finally we have our G to H. Process G to H, which is our, I think volume is constant, G to H pressure is constant, and thing left is only G to H. So we have a pressure is constant. So this is isobaric, and this is quite straightforward now. So we can say work done for G to H will be equal to P dV, or we can say P naught, and this comes as our 8 V naught minus 32 V naught. Therefore we have work done from G to H will be equal to minus of 24 P naught V naught, or their magnitude will be equal to 24 P naught V naught. So we get this Q goes for 3. So we have Q is our 3. Okay. So we were having P is equal to 4 and Q is 3, R is 2 and S is 1. Therefore finally we can write that P matches with 4, Q matches with our 3, and R matches with 2, and we have S that matches with our 1. So this completes all the 5 questions. In this we dealt with 2012 3 questions and 2013 advanced 2 questions. So total 5 questions. Thank you.